Welcome back to another episode of CS 340, Machine Learning Data Mining. I'm your host, Frank. It's your co-host, Bayman. Today we're going to talk about feature selection. Last time we talked about trying to find the true model when we were talking about the polynomial regression, in the polynomial regression sense, right? So what if the output yi really is a polynomial function of the input xi? Is it like a reasonable thing to even think about trying to find the true degree of the polynomial relationship, right? And we, I think at this point, all understand that if we try to simply, minimize training error, that's not going to work because basically training error will go down as the degree of the polynomial goes up, right? And we talked about the fact that cross-validation might not even work because it will tend to slightly overestimate P due to optimization bias. So for instance, if the true model, if the true input-output relationship is actually a second-order polynomial with this particular form, 2xi squared minus 5, but notably plus some specific noise, right? Then you might choose one of the higher order polynomials that just happens to fit that noise a little bit better by some small amount of mass put on one of the higher order terms. Okay, so that might not necessarily work. Such a model might get slightly smaller validation error, right? Last time we talked about complexity penalties, right? So we talked about putting a penalty directly on what we call model complexity. You can think of it as model expressivity, so on and so forth. The idea is that we want to fit the data while fitting it with the simplest possible model that actually achieves our objective, whatever that happens to be. So we talked about some score function, which in particular was parameterized by the degree of the polynomial, and this is what we're going to use for model selection, so to speak. There's a strength of the penalty term, there's some hyperparameter lambda, then there's a number of degrees of freedom, k equals p plus 1 for a degree p polynomial, the 0th order term as well. And then you have the usual regression error, noting that the feature matrix is actually a function, the size of the feature matrix, and in fact the values in the feature matrix are a function of the polynomial degree p. And the idea was, we put this in quotes last time, that in order to make the model more expressive or more complex by 1, right, make the polynomial grow by 1 order, in order to justify that under this scoring function, we need to decrease the error by at least lambda, whatever that happens to be, right? And such a penalty prefers smaller degrees of freedom. It prefers less complex, less expressive models, particularly if the errors are similar. In other words, this term is similar between the two. It's always going to choose the one with the smaller score. Problem is, though, we can't optimize this using gradient descent since it's discontinuous in P. It jumps by a factor of lambda every, P 1, 2, 3, 4, whatever it jumps up by lambda, right? That's pretty clear. Plus whatever the score is. So we can't optimize this using gradient descent. So we have to search over the values of P. Right. There are lots of versions of the score. We talked about a few of them, right? One that we didn't particularly settle on, we'll talk about it right now, is that a disadvantage of these kinds of methods is that as n grows, as the data gets more and more expressive and there's more and more noise and so on and so forth, right? Generally, they will prefer a larger polynomial, even if the relationship is actually lower order, just because there's more data. this term will start to dominate, right? So one solution, a very common solution, is to make lambda, the choice of this value right here, make this thing a function of n. Okay, so make lambda depend on n, and the Bayesian information criteria uses this, right? And this is where compression really comes to the fore. I know this section has been really into compression, right? Because, yeah. Anyway, so the Bayesian information criteria uses lambda equals 1/2 log n. And this means that it penalizes a little bit more than the IKK information criteria for large n. This then goes to infinity. This recovers a true model. It's consistent for model selection. In practice, though, what we actually do is we just try a bunch of different lambda values, and whichever one works the best for our particular application, that's the one we go with. It's like a hyperparameter, like picking k and k means. Right? And there are other scores. There's elbow methods, which corresponds to choosing a specific choice of lambda. Methods based on validation error rather than test error. Take the smallest p within one standard deviation of the minimum cross-validation error, blah. There are all sorts of things, but really what you should think about is maximizing evidence or marginal likelihood in a Bayesian modeling context.
Is there a quantitative way to do the elbow method, or is it usually human-based?
Usually human-based. And these can be adapted to different norms. It's not a problem. Okay. But yeah, that's the story there. Let's go back to our motivating example, discovering food allergies. If you remember, I'm allergic to everything. And let's just put a couple of other items on there, because as far as I'm concerned, taco is a foodstuff, and Tuesday might be a foodstuff as well. This will make a little bit more sense later on. So I can eat 2 tacos or 3 tacos or 0 or whatever. And it's going to be Tuesday every time I eat tacos, most of the time. Okay. I've got the food allergy example. This is what I eat on a day. This is how much of a particular substance I eat, and this is whether or not I have an allergic reaction. I get sick, right? So maybe this is the subject of the lecture today, and this is an annoying thing that you will be asked in industry to do sometimes, right? So we've sort of, we're on this journey together where we think about models, and then we think about how to make those models more awesome by adding features, and then we think about problems that arise from that, and then we think about ways to control the complexity of models, right? And you can start to see that the polynomial, like whether or not you add particular features, that's actually a model choice. It's a model complexity choice. So you're actually choosing amongst models, right? And now that there's this really waffly business in between yesterday and the lecture on Friday, where we have to think about maybe one of the things we might want to do is actually do feature selection. Like we want to figure out what the right features are for our application. Now, this is a little bit antiquated in some sense, but it's actually something you'd be asked to do relatively frequently in real situations. And it's pretty super annoying because it's difficult to do. It's hard to even just define what, you know, a relevant feature is. But anyway, let's pretend that that's what we're going to do. Instead of predicting, instead of actually solving the prediction task, we want to actually figure out which features are relevant for doing this, right? In this particular case, which foods are relevant for predicting sick. And this is really the same thing as model selection, but you know, feature selection, model selection, same thing in my estimation. But we're going to talk about it in terms of feature selection. So the general feature selection problem looks like this. We have our data matrix X. Really, probably in your head, you should be thinking about Z, because you know we're going to be saying, okay, there's a whole bunch of features that we could choose. So, I mean, it could be X or Z. It doesn't really matter. We're going to choose a bunch of features, and we're going to try to decide which columns J are important for predicting Y. Right? You can say, what are the relevant factors? Which basis functions should I use amongst these choices? Which types of new data should I collect? And obviously, if you can say, I don't care about all these features, I don't need them, they're irrelevant for my prediction task, like there's an ID feature or something like this, or day of, day of week, who knows, whatever. Tuesday was an example, it's not a good one. There's an ID or like temperature column in the allergy case. So you would just say, those are irrelevant, let's get rid of them, we don't need to pay attention to them. That's going to speed up computation in all of the models we've considered, right? And I would put here applied, right? So it's one of the most important problems in applied machine learning or statistics. People have spent a long time thinking about it from a research perspective as well, but it's super, super messy, partially because the definition, and we'll talk about this at the end of the lecture, and a bunch of tan slides where you can relax and think about how to finish your homework on time. But for now, what we'll say is that a feature is relevant if it helps predict our output from our input. Okay, that's good. A reasonable question to ask at this point is, shouldn't we be able to set up models that use all the features regardless of whether or not they're good? Well, that's basically starts Friday. Okay, so today we're going to say, well, what we want to do is we really want to find the ones that are helpful, right, and actually predictive. So one way you could do this is to take an association approach, right? It's a super simple and reasonably common way to do feature selection. And it's straightforward. Basically, for each column J in your data matrix X or Z, right? You pull that out and you compute the correlation between that vector and Y. Okay. And you say that the feature J is relevant if the correlation is above 0.9 or below negative 0.9. So it's highly correlated or anti-correlated. Anti-correlated features are just as good because you put linear weights on them that are negative, and it's fine. Okay, cool. Basically, this turns feature selection into some sort of hypothesis test for every feature. There are lots of measures of dependence. Unfortunately, the association approach, although it is common and it's certainly simple, usually gives unsatisfactory results in the feature selection sense because it ignores, for a number of reasons, but one is that it ignores variable interactions. So, it includes irrelevant variables, right? So in the case that I already hinted at in the allergy example, right? If there are two columns there, one of which is eating tacos and the other one is it a Tuesday or not, right? If tacos make me sick, which they don't, thank God, and I only eat tacos on Tuesday, which I don't, unlike my parents, they only eat them on Tuesdays, it will say that Tuesday is relevant, which is totally obviously not true, right? The day of the week is not going to cause me an allergic reaction, although I do seem to be allergic to Mondays. And this association approach excludes relevant variables, right? So again, if you had a Diet Coke column and a Mentos column, right? The two of them on their own don't make you sick, but together, this togetherness thing is the problem. They'll make you sick, but the association approach will only pick out individual features, not combinations of features. Association, this association approach is actually quite common in the physical sciences. In particular, there are these genome-wide association studies, right? And they can be used to measure whether or not there's there exists a dependency between an individual genetic mutation, a single nucleotide polymorphism in the gene, and a particular disease. So here's a position along a chromosome, an index in the genetic code, and this is the p-value on a test as to whether or not a single nucleotide polymorphism or a change in the genome there is correlated to a particular disease, right? And this association, approach to doing feature selection has identified thousands of genes associated with diseases, and it's by design set up to have a large number of false positives. In other words, not all of these particular genetic defects are going to be associated to the disease, but it gives you a method for screening through features that could be related to the disease of interest. Another approach to doing feature selection or identifying relevant features is actually to just fit a regression model and look at the regression weights that come out. Okay. It's also simple, it's also common, it also has problems, which we'll talk about. But it is a way to do feature selection. So basically you fit a model, right? You get regression weights based on all features, all the possible imagined features for Z and or X. Maybe you use least squares, maybe you use something else, right? And you just decide that you're going to take all the features where the absolute value of the weight is greater than some threshold. And you should do this in a post hoc way, which is totally a weird thing to do, but that's what you do. You fit them, remove everything where the weights are smaller than some threshold, and you go. Clearly, this is going to give you a more robust model because it's going to be a simpler model, right? And that threshold again can be a hyperparameter that you search over, right? So again, okay, great. So Raymond is responding to my sort of flippant point that if you already fit it, it seems a little bit weird to choose. So that's not exactly fair, actually, of me to have said, because the aim of there's multiple aims of doing feature selection, right? So one aim is to say, we're trying to figure out the features that are responsible for good predictions, right? And the benefits of that are, it's a faster model, or it's maybe the one that we really want to think about is it will be more regular. It will be a simpler model, right? And in fact, in that sense, this regression weight approach is a very good idea, because if you remove stuff that has very, very small weights on it, those are likely those small weights are likely to vary quite a lot from one data set to another, which means that they're kind of probably going to be used to fit little teeny tiny little details in the data. So if you get rid of them and then refit again, the resulting model will be simpler and will ideally generalize better. And to be really concrete about this, you can fit, if we have a feature matrix with 5 features and we fit a least squares model and we find these particular features, then the absolute value of the weight here, it's pretty clear that that's pretty relevant, right? Feature 4 also looks relevant. Feature 5 probably not relevant. It's not actually really strongly involved in the value in producing the value of the prediction, right? So this kind of regression weight approach could actually, in the Taco Tuesday example that we put out there, could recognize that Tuesday is irrelevant, right? If you get enough data, if you get enough rows in your data matrix, right? And in fact, sometimes you observe that tacos are eaten on days other than Tuesday, and the relationship is actually linear, then this kind of regression weight approach could work out that that the regression weight on Tuesday is going to be small, and the regression weight on taco will be large just from the data. And it could definitely recognize that Diet Coke and Mentos together are relevant, right? Provided that this combination occurs enough times in the data such that both have high regression weight simultaneously when making the prediction about whether or not one would be ill. Exploding stomach, I suppose. Unfortunately, it has pretty major problems with collinear features, right? So going back to this Taco Tuesday example, like if the Tuesday variable always equals the taco variable, right? It could say that Tuesdays are relevant, but tacos are not, and that's clearly uncomfortable in terms of what we would naturally think about in terms of what a relevant feature is for making a prediction about a food allergy response, right? Tuesday is clearly not a food, so it'd be weird, right? So in other words, we already talked about this, right? Any regression model that we learn with values of W1 and W2, if taco and Tuesday are perfectly correlated, then, I mean, this is an equivalent model and there's no taco in this at all, right? Just a non-food thing, the day of the week, right? And worse yet, if you have two copies of an irrelevant feature, it could make both irrelevant copies relevant, right? Because this model, if it's a perfectly collinear feature, is the same as this model. Like these two very large weights cancel out in the end, and who knows? Maybe that's what your gradient descent procedure would arrive at. Right? This is an equivalent, one of the equivalent global minima. Right? Okay. I always love this Taco Tuesday example because I recognize across the awesome, and I actually mean awesome, cultural spectrum of the students who come to UBC and sit in this class and that sort of thing. Like the idea of Taco Tuesdays, so North American gross. It's actually something that my parents do on the farm in Illinois. It's like, the tacos are terrible. It's Tuesday and it's just all wrong. Anyway, so any questions at this point? Should be pretty straightforward. This is a pretty easy lecture today. I wonder, that's a good thing. Are there what are the cultural equivalents in other cultures of Taco Tuesday?
I would say I'm from Iran, so we have something similar. And Fridays, I would say, I don't know, it's a special meal sometimes we have.
No, it's got to be like, the thing is, it's got to be like cheap, some cheap non-national, it'd be like, shawarma Thursday in Italy or something like that. I don't know, like what it would be, anyway. I'm sure that such things exist. It would be, I thought maybe some would scroll along the comment section. I won't repeat that out loud in case the Trumpistan police come and get me. Anyway, so that's it. Hopefully that's lightened your day slightly by thinking about these things. Anyway, so the most common feature selection framework is some sort of search and score framework, where we define some sort of score function, we'll call it f of s, that measures quality of a set of features, right? S. And some sort of way to search through variables or features S with the best score. Okay. So if we have 3 features, I like to think of S as a subset of all possible features. That's really the way I think about it. But you can think of it as there's just some set of features and we're gonna search for stuff. So the way I think of it is subsets though. So we have 3 features. The way you do some sort of search and score, if you were to do a global optimization, you would compute the score using feature 1. Basically, you'd fit the regression model with using one feature 1, compute whatever score it is you're computing, compute it with feature 2, feature 3 alone, then compute it with the pairs, then compute it with everything, all the features, and then compute it with no features, right? And then return the set of features S with the best score, whatever that happens to be. Straightforward, right? Okay. But a couple of things to look at: the size of the search space is 2 to the D, right? There's a lot of options, which automatically in your head, based on the fact that we just immediately jump to greedy algorithms, you should be thinking, we're probably going to see a greedy algorithm for optimizing for searching in such a space. Right, so what's the score function that we use? Well, the score function can't be the training error. The training error goes down as you add features, just like in the polynomial regression case, right? It's a little bit less obvious that that's the case. If you think about it for a second, though, it's sort of clear that that's what's going to happen. So basically, if you just look at the training error, it's just going to select all the features and put little teeny tiny weights on all of them, right? Just to fit all of the error. A more logical score is the validation error, right? That would find the set of features that gives us less validation error to minimize the test error. This is what we want. But there are some problems, right? Due to the large number of sets or subsets of variables, right? If we have D variables / features, there are 2 to the d subsets of such variables. So the optimization bias will be high. We're optimizing over a very, very large number of models, 2 to the d models, right? Not 10. And this means it'll be prone to false positives in the same way that the polynomial regression case is prone to false positives. In other words, you will very likely add variables that actually are not really helpful, but sometimes help by chance, just because of the particularity of the validation set. So in other words, in order to reduce false positives, and this is a kind of a little bit of an ass backwards, did I just say that? I meant to say bass backwards, that's what I meant to say, way of getting to this. The number of, in order to reduce the number of false positives in the way that we just talked about here, we can again employ complexity penalties, right? So here we have a score. This is a standard regression, loss that we're used to seeing. Note that the parameter vector is indexed by set. The set here really, that's important, right? And the feature vectors are indexed by set as well, because they're going to be different for the set of features that are used. This is the size of the subsets, the number of features out of all possible features that we're using. And the score is going to look a lot like one of the complexity scores that we've seen before, complexity regularized scores we've looked at. In other words, we can use the squared error, number of non-zeros. And here we're using XIS as the features, S of example, XI, right? So clearly if 2 SIs have similar errors, in other words, this term is the same between the 2, right? It's going to, by selecting models based on their score, it's going to prefer the model that has the smaller set, because this term will be smaller for the smaller set of features. For example, if you have some weight on a feature that's very, very small, and it doesn't really affect the score, it might choose to actually remove a feature. In other words, simplify the model rather than keep in a very low weighted feature. Right? And instead of size S, which is a fine thing to write, we actually usually write L0 norm. So what does that look like? Well, the L0 norm is related to the number of features that we use in the following sense. In linear models, and this is obvious, but we're thinking about setting one of the regression parameters equal to 0 is the same as removing the feature, right? So if you set W2 equal to 0, then feature X2 goes away, right? So the number of zeros in your feature vector corresponds to the more zeros you have, the less complex model you have, right? The L0 norm is is defined everywhere to be the number of non-zero values in a vector, right? So the L0 norm of the vector W, these are the regression parameters, is the size of the parameter set, of the feature set, that straight up, right? So for example, if W happens to be 1, 0, 2, 0, 3, right? Then the L0 norm is 3. If it's all zeros, then the L0 norm is 0. It's not actually a true norm, but if W has a small L0 norm, then it doesn't use very many features. It's fine. So this is basically what we're gonna play with to do feature selection. I'm gonna put an L0 penalty on. That's going to control the number of degrees of freedom. It's like controlling the number of degrees of freedom of the polynomial regression model. Right? We have the training error here as always. And let's say that we want to use this to evaluate the features S1 and 2. All right, so we fit W here using just features 1 and 2, and we compute the training error with this W and the features 1 and 2, obviously, because that's what we did. And then we add lambda times 2 to the training error to get the final score. And we can repeat this for other choices of S to find the best or most relevant features, okay? Now the question is, which other choices of S? What is our search space? We're not going to try the exponentially large number of models. That's not possible, right? Cool. before we get there, let's think about what the interpretation of this L0 penalty is, right? So the L0 norm penalty for feature selection balances between the training error and the number of features that we use, right? So if this goes to 0, we get least squares because this goes away. We get least squares with all the features, right? If lambda goes to infinity, then numerically this is irrelevant. And what we're trying to minimize is the L0 norm of a vector. And the way you do that is you put zeros in all of the entries, so you will use no features. Okay. For lambda in between in this range, this penalty balances between the training error and the number of non-zeros. Larger lambda puts more emphasis on having zeros in W, more features removed. And the nice thing is that all the stuff that you might read about, you know, feature selection and so on and so forth, AI, CPSC, so on and so forth, correspond basically to two different values of this lambda. This has all been kind of a long-winded way to get to what almost everybody does when doing feature selection, which is some sort of greedy search heuristic in the combinatorial space of models, almost always using forward selection. There's backward selection as well. We'll talk about that in just a second. You know, in search and scores we defined, it's hard to search for the best S. There's this combinatorial optimization problem, right? So the greedy search procedure or optimization procedure that most people use is forward selection. And it's as obvious as it would seem, right? So you compute score if we use no features, right? You just make a prediction, right? The mean or the whatever. Then you start adding features one at a time, and you compute the score of each one. Fit the regression model, compute the score. Fit another regression model with one feature, next feature, compute the score. So on and so forth. And let's say that, you know, milk is the winner. It got the best score out of all of them, right? Great. Then you go through and you start adding stuff. So you fix milk in your feature set, and then you start adding other features, .go, egg, so on and so forth. And you compute the score of each variable in combination with milk, and you keep the best one. So let's say that egg happened to be the winner. We add egg, we got the best score. So then you start adding more features, you know, you fix milk and egg and you start adding another feature and so on and so forth until some stopping criteria is hit. So that's basically what's happened here. You start with an empty set of features. For each possible feature J, you compute the scores of features in S combined with feature J. You find the J that has the highest score when added to S. You check if the union improves on the best score so far. If it does, add S to J and then go back to step 2. And you can, if it doesn't, then exit. Variation is to stop if no J improves the score over just using S. Obviously, this is not searching over the entire combinatorial space, so it's not guaranteed to find the best set, but it reduces many problems. First of all, it only considers a quadratic number of models in the number of features rather than exponential. It's cheaper, obviously, as a result. It overfits less in the overfitting to the validation set sense, and as a result has fewer false positives. So it's good. You can do the same thing, but backwards. You can start, you can start with all features and you compute the score after removing each feature. And you remove the one that improves the score the most. That could be a little bit confusing, but recognize that you have the regularization term there. So removing features can actually cause the score to go up. Any of these forward or backward selection, feature selection algorithms, when you remove one at a time, it's called stage-wise. There are other ways that you could think about solving this combinatorial optimization problem. Stochastic local search is one of them. You can think about, you know, basically just making random modifications to the feature set that's currently in play, testing that random step, and if it's better, you go there. If not, you stay where you are, and you just do this for a long time, and eventually you'll kind of walk to a good set of features in this combinatorial space. And there's recursive feature elimination is the name for another related method where you fit the regression model, where you prune features with small regression weights. then you do this all over again.
Will forward and backward selection return the same results?
No, not necessarily. And why do forward and backward? Why not do forward and backward to see which combinations are best? So, yeah, you can do all this stuff, and people have done all this stuff, and it makes a lot of sense. If that's what you want to do, go for it. What we're going to talk about in just a little bit, though, is the problems with deciding. Oh, that's a good question. Sorry, the last question made me think. Yeah, you can do forward and backwards in various combinations, but the definition of what a relevant feature is somewhat complicated. Can we approximate the zero norm to make it differentiable? Yes. Yeah, it would be really gross to do, but you could do it. You could take you could take a concrete distribution or a continuous Bernoulli. Like continuous Bernoulli. Yeah, I mean a concrete distribution and its simplification. You could do that. Yeah, you could do that. But there's a little bit weird. The known differential approximations are only valid in the limit, and it's very unclear what it means when that's a good question. I'll have to think about that. It's yeah, there's some suggestions. Yeah, so indeed, it would be some construction like that you would do. It doesn't. The relevant work for that doesn't immediately spring to mind. It's a little bit complicated because when you zero out the weight, what you really want is to just zero out the entire term, including the feature value. Yeah, it's complicated. I'm sure that there's something out there. I have to think about it for a little bit and spend 5 minutes Googling it. It's not that big of a deal, but good questions. Well, so the question is, what's the time complexity of the regression weight approach? Do you mean the recursive feature elimination or the regression weight approach? Right, the time complexity of the original regression weight approach is the time complexity of fitting the regression model and then removing some weights. This is the time complexity of fitting the regression model some unknown number of times until some it's just basically the cost of fitting linear regression some number of times, where you don't know exactly how many times you need to fit it because you don't know how many times you're going to prune off features. Cool. Thank you very much for your interaction and questions. It's great. Wonderful. So the last bit, you can, you know, make another cosmopolitan or whatever. It's just, these are all tan slides, so you can relax and enjoy it. The question is, and it sort of calls into question what we've been talking about in this lecture in the first place, although you should be somewhat suspect because we've said that what we really care about is predictive accuracy. We don't really care about any of the interpretation stuff, and relevance is clearly one of those things. Like the question is relevance clearly even defined? So let's consider a supervised classification task. We're going to start talking about problems with trying to figure out whether or not relevance is clearly defined. Okay, so this is going to be our standard in items here, and this is going to be item I equals 1, and this is going to be D equals 1 and D equals 2, and or whatever J equals, sorry, and this is going to be D long, so D equals 3, N here equals 4. Great. And the task is whether or not somebody has a particular genetic variation or mutation, a single nucleotide polymorphism, right? Here's the RY. This is what we want to predict, whether or not somebody has a particular mutation, right? And let's assume that the location of the mutation is in the mitochondrial DNA. So that means that you almost always have the same value as your biological mother, okay? Great. So recognizing that there are all kinds of different families, including some in my own family, for simplicity here, we're going to use 1950s style language about gender and parentage just to keep things simple. For each individual here, right, this is their biological sex, I guess we could get away with this, but we're going to call it gender. So this is a female. Her mom has the genetic variation. Her dad does not. She has the SNP, right? The mutation. Mom has it, so on and so forth. Okay, great. Female, mom doesn't have it, doesn't have it. Okay. The true model, we actually know here, and this is one of these situations where the true model is something that we should know, right? The true model is basically with very high probability you have, or each individual person here has the genetic signature of their biological mother with very high probability. So basically these are going to be equal except when there happens to be by chance a genetic mutation in exactly this particular mitochondrial DNA spot. Okay, cool. Awesome. So what are the relevant features for this problem, right? So these are the features that we'd like to select from, right? So clearly, just to be clear, clearly these are not relevant features. Like the gender of the person doesn't matter at all. Whether or not the dad has the genetic defect doesn't matter at all. Only the mom, whether or not they have it because of the mitochondrial passing, right? So mom here, whether or not the mom has the biological mother has the particular mutation, that's the only thing that's relevant, and gender and dad are not. Right? So what if we happen to get a data set that has the mom feature duplicated, right? So which one is relevant? Are they both relevant? Should we pick them both? Should we pick one because it predicts the other? Obviously picking neither of them is, like neither of these options are correct, but not picking either is incorrect either, because if you didn't pick these, then there would be relatively little signal to make the prediction on, right? So this is a general problem that shows up in terms of dependence of collinearity for linear models. We already talked about this, right? If features can be predicted from each other, so this is just one, this is 1 times mom, right? Can be predicted from other features, you don't know which one to pick. Okay, so if you really care about which ones are really the relevant features, like, I don't know, one of these two, some combination of both, it's uncomfortable. Right? What if we add the maternal biological grandmother? Interesting, right? Is grandma relevant? Well, obviously, since she's the maternal grandmother, her signature is going to be shared by the mother, and this is going to be shared by the individual, right? So you can predict the genetic mutation, this single nucleotide polymorphism, very accurately from the grandmother alone. But if you know the value of the mom column, right, the grandma column is irrelevant. You don't need to know it, right? So there's a general problem of conditional independence. Like in the generative model of the data, if you know mom, then the value of grandma is irrelevant. Doesn't matter at all, right? So is it relevant? Probably not, right? So relevant features may be, and this is the critical thing, relevant features may be irrelevant given other features. So this one becomes irrelevant because you know the value of this. And if anybody knows graphical models at all, what we have here is if you know this, then this becomes conditionally independent of this. Okay? What if we don't know mom, right? Well, now grandma is definitely relevant, right? We don't have the mom column anymore. We've only got the grandma column. Then using grandma is the best you can do. Right, this is the same problem we were talking about with Taco Tuesday. If you remove the taco column and all you've got is the Tuesday column, and I only eat tacos on Tuesday, then it becomes, then the day of the week becomes relevant for predicting my allergy, which is a weird thing, right? What if we don't know mom or grandma? Either one, both columns are gone, right? So, whoops, there are no relevant variables now, right? Maybe, right? So, dad and mom must have some common maternal ancestor, that's how, humans are made. We know mitochondrial Eve, is estimated to have existed around a couple 100,000 years ago, right? The mom of us all, right? The great grandma of us all. Right? So we have a general problem, which is the effect size, right? So relevant, so maybe actually, the father's genetic makeup is relevant, but it might have a very small effect because there's a latent path between the two. It's quite deep. So yeah. It also could be the case, right? That the particular genetic variation causes some sort of pheromonal, attraction, right? And dad and mom got together because they smell good because they have the same genetic mutation, right? So then the dad becomes relevant, or rather the dad's genetic makeup becomes relevant for making the prediction, but it's not relevant in the scientific sense because there's a confounder, the fact that there's a shared, there's an attraction between the two, okay? What if we had siblings? Obviously a sibling is going to have the same SNP pattern as you because their siblings have the same biological mother, right? It's relevant for predicting, but it's not the cause. So the general problem here is that a relevant feature may not be causal, or it can actually even be an effect of the label, right? Right. What if we don't have mom, but we have baby, right? Baby is relevant when the gender is equal to female, but not relevant when the gender is of the individual is male, right? Because it won't be passed along if the gender of the individual is male. It won't be passed along. Who cares? Baby is no longer relevant, right? But if the gender of a person is female and you know the genetic makeup of the baby, then you know something about the genetic makeup of the mother. So baby is relevant in this particular case, so the causality is reversed. And what's worse is it makes gender relevant when it wasn't before. Okay. This is all a very long-winded way to get to saying basically that when you're doing feature selection, which you will be asked in industry and in reality to do feature selection, there's some things you have to have in mind. You need to know this stuff and go back to it, right? So like a feature is only relevant in the context of other available features, right? And in fact, even worse than that, adding or removing features can make features relevant or irrelevant, right? Confounding factors can make irrelevant variables the most relevant, right? If features can be predicted from other features, you don't know which ones to pick. That's the collinearity thing. A relevant feature may have a super tiny effect, right? If you've only got info about the dad's genetic makeup, there's still some distant relationship a shared grandma. And definitely relevance prediction for prediction. And this is really maybe the most important thing is, you know, when we're always very careful about saying causality in a class like this, because we don't say anything about causality ever, right? So relevance for prediction does not imply a causal relationship, right? So that's really important. So is it hopeless? Well, we have to do feature selection. Sometimes we got to try. Different methods are affected by different problems in different ways, right? You know, some problems have, you know, wrong answers. They don't necessarily have right answers. So the variable dependence thing, right? You know, mom and mom do have the same information. You should take one. Conditional independence, grandma is irrelevant given mom. You should take one of them. Some problems have application-specific answers, like the tiny effects thing. You can look for such features. But in summary, we're running out of time, so let me summarize. Wind up. So feature selection, the task we consider today is the task of choosing the relevant features, whatever they are, where relevance is complicated to define. So there's some obvious simple approaches, and they have obvious simple problems. Search and score is what you really do. You find features that optimize on score. L0 norm penalties are the most common scores. And forward selection is used probably the most. It's a heuristic to search over search for a smaller set of features and search over a smaller set of possible models. All the tan slides at the end are basically just to point out that relevance is actually really hard to define, and like doing feature selection might not even be a valid exercise in some sense, right? You have to be really, really careful. So this sets us up for Friday, where we get back to good old machine learning, and we say, you know what? Let's just do really, really good, even if we have a lot of irrelevant features. And that's what we'll do on Friday. So thank you so much. Questions? And then how do feature selection methods we covered compare to L1 and L2 regularization? So L1 and L2 regularization are explicit. Well, okay, so have we done L1 and L2 regularization? We've done L1 and L2 loss functions, but we haven't done L1 and L2 regularization. So that's an unfair question. So I will leave that until Friday or later. How long is this midterm expected to take? Forever and ever. Well, it'll take some time. It's gonna be good. It'll be good. It's a good learning experience. It'll take, you know, how many hours? I don't know. If you're really good, 4 hours, 5 hours. If it's really, really, if you're, you know, if you struggle with some of the concepts, it could take a while. It's take home. I'm going to do a lot of stuff. How many questions would be included? Any rules for the Kaggle thing? The rules would be on the Kaggle competition. And how many questions would be included? Millions and millions. I think there are 2 questions, but they're, you know, they have many, many parts. So I don't know exactly what the answer to that question is. And you got to do 2 different things in a bunch of different ways. Is there any sample midterm? No, because we've never been doing this in a pandemic. One part of the midterm will allow groups, yes. How big can the groups be? We're still deciding. The TAs want 5, I want 3. It'll probably end up being 5. But the groups can't be the same for the midterm and the final. So you have to decide whether or not you want your, how about groups of 150? Yeah. No, you can choose them. They just can be. They just have to be non-overlapping. So you can, pick your poison. Decide to have your super strong group for the final or your super strong group for the midterm. They don't have to be friends. It's a good way to make friends, actually, based on my experience. Or to make enemies forever. That's also happened to me. Will doing it with fewer people be significantly harder? Group work is a complicated thing. It's part of everyone's education, figuring out how to do that. Yeah, okay. Yes, if you've been in business school, then you really understand. Yeah. Yes, I said only one part of the exam is in groups. That's correct. That will be the Kaggle competition part. So many questions about the midterm. What about learning? Do we get prize money? You get the satisfaction of participation and a degree from UBC. How is the Kaggle portion graded? Carefully. We're going to be looking at your code. Oh, Alan, what a question. Are we ranked for grades? You're always ranked for grades. That's the hidden truth of all grading in all courses. You're always ranked. Okay, this is devolved slightly, so I'm going to propose that we adjourn for the day, and I'll see you all on Friday.